3, so I'm turning on. Thank you very much. Please go ahead.
Okay, thanks a lot for the introduction and thanks for having me in the seminar. I'm happy to give this talk on results that we just got prepared for Neutrino and that we are presently writing up for submission. So in order to give a little bit of an introduction, pretty much where this story begins is back in the 1930 with a very famous letter from Wolfgang Pauli, in which he starts addressing his colleagues as liebe radioaktive Damen und Herren, dear radioactive ladies and gentlemen. And in this letter, he suggests a solution for the following problem. In beta decay, a continuous energy spectrum was observed for the electrons, but since at the time the neutrinos weren't known, in principle through energy and momentum conservation, a single line was expected. And so to remedy both statistics and the conservation of energy and momentum, he postulated that there should be another particle, which he called the neutron at the time. And so it should be a spin 1/2 particle, and this could explain this continuum spectrum that was observed. So by now, we know that this was a very good idea. And in fact, the name has changed from neutron to neutrino in the meanwhile. And so for an electron, we are getting an electron antineutrino in each beta decay. Now, since then, the situation has evolved a lot in our knowledge of neutrinos, and in particular through oscillation experiments, we have learned that neutrinos are somewhat different from the other particles we know. And we have come to understand this paradigm where we have neutrino mass eigenstates, and separate from those, we have the flavor eigenstates. And so we have a neutrino mixing between the mass and flavor eigenstates. Also, very much unlike all other direct particles that we have, neutrinos are very light. They are 6 orders of magnitude lighter than the other particles that we know, than the other leptons. And then in addition to that, back in the 30s, there was theoretical interest in looking if you can make another, if you can derive other solutions for the neutral leptons. And so m.w.e. published another seminal paper in which he postulated a symmetrical theory of the electron and positron, which avoids the negative energy solutions out of the Dirac theory. It's a minimal change, but it has some fundamental consequences that Furey and others found. And so one of the consequences is that neutral leptons can be their own antiparticle. And so in that case, we can go to another process that Maria Goeppert-Meyer kind of investigated, which is the double beta decay process. And so in a normal double beta decay process, we would have one vertex here with a d quark changing to a u quark, and then getting an electron antineutrino and an electron. And then a similar vertex with another electron antineutrinos, and then ending up 2 electron antineutrinos, 2 electrons in the final state. And if we were to record the energy, we would measure the electrons and we would measure this continuous spectrum over here. Now, taking Majorana theory on the other hand, there is this, and we know that the neutrinos have masses, then the only distinguishing factor between the antineutrino and the electron neutrino is the handedness, how it interacts in a vertex. So we have the left-handed antineutrino, and then we would just need to interact right-handedly in the second vertex, and we could reabsorb this neutrino. So there could be this Neutrinoless double beta decay mode, which changes lepton number by 2. So it generates 2 leptons. And this in combination with the fact that there are processes known which can convert lepton number into baryon number differences, also connects this mechanism, or hypothetically connects this mechanism to matter generation in the universe. So it's a very interesting theory, which on the one hand side connects to the lightness of neutrino masses via the seesaw mechanism. On the other hand, possibly also connects to leptogenesis and baryogenesis. And so as an experimentalist, what we would be looking for is, instead of this continuous spectrum, if we measure the entire energy in this decay, we would measure the full energy of the electron. So we would measure a line at the end point, which so far hasn't been observed, but in our case, in 100 molybdenum would appear at 30 or 34 keV. And so from looking at this Feynman diagram, we can also look into how this rate is given. And so we have some particle physics, the phase space factor, then a nuclear matrix transition element for the nuclei in question. And then from neutrino physics, we have a single parameter, which is the effective Majorana neutrino mass in this kind of picture of the Light Majorana neutrino exchange. And so this is this parameter is simply given as the sum over the neutrino mixing parameters times the individual masses, where the mixing parameters over here are extended in the Majorana theory by two complex phases. So if we look at that from an experimental point of view, we want to kind of look at the numbers that go into here. And so the first one is precisely calculable, the phase space factor. And while precisely calculable, dependent on the endpoint, dependent of the full energy and the decay, there is up to roughly a factor 10 difference in the rate that we can expect. So some are slightly more favorable than others. Then if we look at the nuclear matrix transition elements, there we are looking at heavy nuclei. And for those with all of the shells and the configuration of protons and neutrons, it's very hard to do the calculations. And so all of them have to take some approximations. And hence right now, while there's not a very large discrepancy between different nuclei, there is still a spread of a factor 2 to 3 in the knowledge of this transition element. And then when we take those, when we measure the rate, we effectively usually transfer this into a measurement of the effective Majorana neutrino mass to compare against other experiments. And so we plot this effective Majorana neutrino mass against the lightest of neutrino masses. And so while there has been lots of progress in neutrino physics and oscillations, there are still some big unknowns. And so while we know, for example, the mass splitting very well between m1 squared and m2 squared, m2 squared to m3 squared, the large and the small one, as well as the mixing angles, we don't know the ordering very well yet. We have hints that the normal ordering is preferred, but the inverted ordering is not ruled out at this point of time either. So if we go back and look at this formula of the effective Majorana neutrino mass, which is the sum over the mixing matrix elements, then, oops, sorry about that. Then essentially, since some of those parameters still have some uncertainties, but mostly we have these two additional complex phases from the Majorana theory. So for that, we have three masses, m1, m2, and m3, and two unknown angles in this complex space. And so we add up those three, and then dependent on the angles of these two new parameters of these two complex phases, we have a different range of values for any given m lightest that we choose. And so this results in this band over here, and one band for the inverted ordering, the other band for the normal ordering. So in case we were to observe Neutrinoless /β decay at some point in time, there's not only information about the fundamental nature, whether it's a direct particle or a Majorana particle, there's also information about the inverted ordering encoded in that, and or normal versus inverted ordering. Now, so much to theory. Now, to come to the experimental side, so what's the difficulty in this experiment? So right now, current experiments probe half-lives, the leading experiments probe half-lives at the range of 10 to the 25 to 10 to the 26 years. And so I've got difficulties visualizing that number. And so trying to do something in time, it ends up being the age of the universe squared and then multiplied by another 10 to the 5 years. But on the other hand side, we are measuring a decay. So we have Avogadro's number to help us, which is also a very large number. And so maybe a more appropriate comparison here is when we are looking for Neutrinoless double beta decay, and when we are planning our next generation experiments, we are planning them to look for single events in a ton of isotope and a year or years of exposure. So we are looking at activity levels of 3 times 10 to the minus 14 becquerel per gram as our signal. And if we compared it to something which is ubiquitous, or if we look at potassium 40, and in a banana, we are roughly at 15 becquerel per banana. So 15 orders of magnitude lower is what we are looking for in our signal. And that's really most of what our game is about. So experimentally, we have about a dozen candidates that we consider for the search for Neutrinoless double beta decay. And so most of all, they are characterized on the one hand side by a high Q value, which is on the one hand side connected to a high transition probability, high phase space factor. And on the other hand side, a high Q value brings us above a lot of the natural radioactivity. So the most prominent gamma background that we have in these types of experiment is usually 2,8 thallium, the 2,615 keV gamma line. And so in 100 molybdenum, we are well above that at 3 MeV, 3034 keV. And then the other thing that we are looking for in an isotope is that it's somewhat abundant in nature. And there's most of the isotopes are actually quite similar. There is tellurium-130, which is much higher, but lower, which is currently used in CUORE. So molybdenum-100 is in this kind of rather nice spot with decently large isotopic abundance, which makes enrichment cost-effective and feasible, and it's at high Q value. So the technology that we use is scintillating cryogenic calorimeters. So as basic principle, what we do is we embed our material in a crystal, and then we cool this crystal down to near zero in the tens of millikelvin range. And as the heat capacity drops according to the Debye law, these detectors become very sensitive to any minute energy deposits from particles or interactions. And so if we equip them with a thermistor as sensor, and in our case, a neutron transmutation doped germanium thermistor, we can change the temperature rise for an energy deposit into a voltage change that we can read out in our DAC. And so this is the basic theory. In practice, we have our holders here, and then we have our crystal lithium molybdate in the middle. And here we have our sensor, our thermistor, to read out the temperature change. And here we have another resistive element, a silicon heater, to inject known pulses of a given energy to calibrate and to stabilize the thermal gain over time. We use a bolometric germanium wafer as light detector. And so essentially what happens when we have an interaction, in the lithium molybdate is we get scintillation light. The scintillation light is guided by reflective foil to this germanium wafer. It leads to another temperature increase, which is also read out by a neutron transmutation doped germanium thermistor. And here's an example of a calibration event. So from 2615 keV, from 28 thallium, we see we get a quite nice signal to noise in our main crystal absorber. And then in the adjacent light detector, we get a much faster pulse due to the relative stronger coupling and lower heat capacitance in the light detector. In total, CUPID-Mo has been operating from 2018 to 2020. And we were lucky to get a spot in an existing cryogenic infrastructure in the Edelweiss experiment at the Laboratoire Souterrain de Modane in France. So back there, we have 4,800 meters of water equivalent in rock overburden to shield from muons, which reduces the muon flux by roughly 6 orders of magnitude. And then we have the all of the shielding of the Edelweiss infrastructure, which is polyethylene, lead, and then the cryostat with lots of the cryostat part from radio-pure and OvBB copper. During this time, we operated both at 20 and 22 millikelvin, and we have a total of 2.26 kilogram of molybdenum 100 in 20 individual detectors in 5 towers over here. And in principle, all the crystals were operational. We lost one of the light detectors during the initial cool down, but since the crystals are arranged such that they typically see 2 light detectors, it meant we could still use this module. And to give a little bit of an impression of the underground laboratory and the underground environment we are in, this is from one of the collaboration meetings when I was back in the Edelweiss experiment. So it's from the mountain range from Oswa, where we had our collaboration meeting, looking over at the Frejus mountain range. And then on this map over here, on the one hand side, you have France, on the other side, you've got Italy, and then in the middle of the, there's a highway tunnel connecting the two, and in the middle of the highway tunnel, you have the LSM laboratory. So if you go in there, you typically stop here in this kind of like an emergency bay on the right-hand side of the road, and then you cross the highway tunnel, go into this emergency shelter, go through this emergency shelter further down into the laboratory. And so this was from our inauguration meeting, where we had a fairly large crowd visit the experiment. In terms of size, it's much smaller than SNOWLAB. It's a single experimental hall, so we have the road tunnel over here, then the entrance through the shelter, and the Edelweiss cryogenic infrastructure at the back of the hall. Back then we still had NEMO-3, now replaced by the infrastructure of the Super NEMO demonstrator. And so in practice, this is how our environment looks like in the LSM laboratory. So this is a view of the Edelweiss cryostat as the shielding is opened. So it's a slightly curious design with the cryostat geometry reversed. So the helium bath and the dilution unit is actually mounted on the ground floor below, and then we have a cold finger going up to this experimental volume, which makes it easier to access, and which has then these sliding shields on the right and left-hand side that you see over here. About 18 centimeters of lead with the innermost 2 centimeters Roman lead, and then a very thick 50 centimeter polyethylene shield. And in black, you can just barely see our muon veto system of the experiment. The crystals that we have there we were kind of lucky to be able to recycle molybdenum 100 from the NEMO-3 collaboration. So NEMO-3 finished up, they had about 7 kilograms, 7.5 kilograms of molybdenum 100. And between NEMO-3 and CUPID-Mo, we have a few collaborators that are involved in both experiments. In Russia at NIIC, Novosibirsk, we've got our experts for the crystal growth and for the purification of molybdenum. And so we took 2 kilograms, roughly 2.5 kilograms of the molybdenum from NEMO-3. This was purified, and then it was grown in a double Choralski crystallization process into these 20 detector modules that we have, with each one about 210 grams in size and roughly 4 centimeters in diameter. The cutting and polishing procedures are similar to what we do in the CUORE experiment. So essentially, we have a very pure silicon dioxide slurry. The only difference is that lithium molybdate is slightly hygroscopic. So we use an oil-based slurry, and we take some extra precautions to store in a dry nitrogen atmosphere and to ensure that this is not interrupted. In terms of design, having this infrastructure that we can share in also meant that we had to adapt to this infrastructure. And so the design of the CUPID-Mo experiment was made in a way that it was easy to construct at the laboratories outside, and then bring into the underground laboratory and connect into the existing setup. So we have a single detector module here on the left, where you have the copper housing supporting the crystal here from below, with Teflon as the weak thermal link in between crystal and housing. And then each one gets a light detector below and then is stacked into this tower. The towers themselves are isolated from the mechanical environment via springs. And so they are more or less just slightly damped in here and connected to this top plate. For calibration, the downside of having a fairly low density target and having fairly low mass crystals of 210 grams is that we need to devote quite a significant amount of time to calibration in order to precisely determine the energy scale at 3 MeV. And so we calibrate on a 10-day schedule, which is the liquid helium refill schedule of the cryostat. And we typically use 2 days of calibration, 8 days of data taking, which makes for 22% in total calibration over physics data. So our calibration source is based on a thorite stone, which contains both uranium and thorium. So we get 2A thallium-2615 as our most intense high energy line, and then 214 bismuth as several more intense lines at intermediate energies. On the other hand side, for the light detectors, there we are using the fact that there is a high intensity cobalt-60 source that Edelweiss uses to irradiate the detectors and free them of space charges. And so from this irradiation, we are getting X-ray production at a suitable rate to calibrate our light detectors. And so for 30-hour cobalt-60 calibration run, you can see the sum spectrum over here, where you can have the K-alpha line, K-alpha, K-beta line from molybdenum. And then you can also see the copper K-alpha line at lower energy, around 8 keV over here. The ability to calibrate also gave us the chance to understand and monitor our detectors a little better. And so here we have investigated the light yield in keV per MeV of initial energy deposit for 3 different classes. So each detector has a top light detector and a bottom light detector, but then the top of the tower doesn't have the top light detector, so it only has a single light detector at the bottom. So in case we have this reflective copper cap at the top, we see typically the highest light yield here in blue of roughly 0.9 keV per MeV, while for the detectors which are sandwiched between two light detectors, we see 0.6 to 0.7 keV per MeV, with the lower light yield in the bottom light detector given by this copper ring over here, which supports the detector from below. The strength of this technique lies in the fact that we can eliminate backgrounds from alpha particles. And so this comes due to the different stopping and different production of scintillation light dependent on the particle type and the stopping power of the particles. So we typically see that for alpha particles, which is 210 polonium down here, we see about 20% of the light yield compared to beta gamma events. And so at 3 MeV, we have a very clear discrimination between the light for alpha events and beta gamma events. And with that, I'm wrapping up the technology part, and I'm coming to the analysis and the data that we've collected over the last year. So for this analysis, we unblinded for Neutrino 2020. And so we considered data beginning in April 2019 up to April 2020. So 1 year of data, or 380 days total. And in this period, we've got 7 long data sets, which are 1 to 2 month scale and characterized by continuous operation conditions. We have an additional 3 very short data sets, which we excluded from the present analysis because we have to characterize surplus uncertainty in the energy scale in these periods. And so taking these 380 days, we have a total of 240 days of physics data. And then in the 7 long data sets, we select 200 out of those, which makes up for an exposure of 2.17 kilogram years in physics data. The analysis that we do is we record all of the data as streams, and which allows us to re-trigger the data with better algorithms afterwards. And then we store 3-second long pulse traces for both the lithium molybdate crystal and the light detector, and use an optimum filter-based analysis to estimate the amplitudes. In addition to that, we then use a set of cuts, and I'll quickly summarize them here and then exemplify the light yield cut, since this is the most crucial step forward from CUORE to the use of scintillating cryogenic calorimeters. So we have some basic cuts, which is, for example, required that we only have a single trigger in the pulse trace to make sure we have an accurate energy estimate. We require another stability cut for the cryogenic system in the sense that we require the pre-trace to be fairly flat. So it's cut on the baseline slope, we call it. And then we have, since we have 20 detectors now, we place a certain constraint on the multiplicity of an event. So for a Neutrinoless double beta decay signal, we have the 2 electrons from the decay, and we would expect them to be mostly contained in pretty much in 3 out of 4 cases to be contained in a single crystal. While for example, backgrounds from thallium-208, thallium-208 has a lot of gamma cascades, and so it often has also 2615 plus 580 keV as gamma, and so you much more often also get event signatures like this, where you have multiple crystals in one event in coincidence. We use a pulse shape analysis procedure based on a principal component analysis. So it's kind of similar to a chi-square cut, only that instead of using an average pulse to compute a chi-square, we use a principal component analysis to reconstruct the primary components of the pulse, and then compute a reconstruction error between the actual pulse and the primary component of the principal component analysis. And then finally, we've got the light yield cuts that I'm going to talk about, and an anti-coincidence cut with the m.w.e system. For the data taking, the first thing is we evaluate our triggers. And so one of the abilities that we have is this re-triggering that I talked about. And so while we had an original analysis with a derivative trigger, in this analysis, we trigger unfiltered data. So we use our optimal filter to analyze, to filter the continuous stream, and then trigger on that filtered trace, which helped us lower our thresholds significantly. And so now in this analysis, we get a typical lithium molybdate threshold of 10 kV, 90% efficiency, and typical light detector thresholds of 0.5 kV. Then after triggering, going through this analysis, so for 200 days of data, we get the following plot, for example, for discrimination. So here you have the energy of the light detector, and down here you have the lithium molybdate crystal energy. And so we have changed the calibration slightly in this case. So it's a cross calibration of the light detector to record the initial energy deficit. So for beta gamma events, this is cross calibrated to be 1. So 2615 kV gamma would appear at 2615 kV in this plot, while for alphas, we still have this 20% quenching and C alphas down here. This change in calibration is due to the fact that we don't have cobalt-60 calibration data for all data sets, and it is convenient in the sense that we can compute a weighted average of the light yield in the top and bottom light detector to help ease our analysis and help improve our resolution on the light detector. And so the cut that we place is based on our calibration data, and essentially, given that we have a really large gap between alpha and beta gamma events, we designed this cut to be pretty much fully efficient for signal, placing it at 3 sigma on the calibration data. Then in order to evaluate if we really achieve this 3 sigma acceptance that we design, we go from calibration data to physics data. And so there we noticed 2 things. For one thing, we noticed that the original model that we used to model the energy dependence of this cut, which is based on photon statistics, was not well reproduced in data. And we understand that in the fact that other than in the original design, we had to go to a lower sampling, and we observe an excess broadening dependent on the phase of a pulse with respect to our sampling. Still, we see that some detectors show a linear energy dependence, others show more of a square root energy dependence. And so we treat this difference and this excess broadening that we observe as a systematic in this analysis, running toy Monte Carlo models, considering both either a broadened photon statistics model or a linear model. And so this gives us an additional systematic on the efficiency and uncertainty of this cut. And so the typical efficiencies that we get are summarized over here for all of our 7 data sets. And so several of those cuts have an efficiency loss at the level of 1 to 2%. And it's kind of dominated by the principal component and the light yield cuts that we have. And so the total efficiency comes down to 90.5%, plus minus 0.4% statistical, and then the systematic uncertainty from the light year cut of plus 0.9 minus 0.2%, dependent on which model is correct for the excess broadening. Putting all of the data together that we have, we select 19 out of 20 detectors which have a good performance for this analysis. So one with excess noise got rejected. And that together gives us the following two spectra here. So we have in red the uranium-thorium calibration data, and so we normalize that to the peak height of 2A thallium in physics data. And one thing that becomes apparent if we do this comparison is that our background data has this continuous shape over here, which is due to 2-neutrino double beta decay. So even though 2-neutrino double beta decay is a very rare process, it completely dominates our spectrum in the CUPID-Mo experiment. And so this will be interesting for further analysis, since 2-neutrino double beta decay is also a process which is important to understand the transition matrix element for 2Nu, and which has implications for the Neutrinoless double beta decay process. So this signal to noise is something which is quite nice to see. The region around Q beta beta 3034 keV has been blinded, so plus minus 50 keV was still blinded over here. And then we essentially just saw very, very few events, 3 events above that. And that comes to how we try to extract the limit and how we try to search for the peak at the endpoint at 3034 keV. And so essentially, we decided early on to go for a counting analysis in order to minimize impacts of uncertainty in modeling the detector response and extrapolating from our calibration at 2.6 MeV to 3 MeV. And so what we do is we take detector-based resolutions from calibration data, plus we take an estimate of the background index from background modeling, and we put that together with a simulation of our signal in order to define optimal region of interest on a channel dataset basis. And so I'm gonna talk a little bit about each of these steps involved here. So the first one is the energy scale, how we get the precise location at Q beta beta. And so here we have the calibration data again. And so from our calibration data, we have a second order polynomial calibration. Wait, I'm talking, sorry, that was completely wrong. This is our background spectra. So we calibrate, so it was correct in calibration. We use a second order polynomial to calibrate. And we check in calibration data the consistency in time. But then we go to our background data set, to our physics data. And we have, again, this 2Nu shape over here. You have the 2A thallium line, and you see very few contaminations coming up above that. And some of them is cobalt-60, potassium-40, and then bismuth-214 and lead-212 lines over here. We take the following peaks out of those: 2A thallium, potassium-40, and then again 214 bismuth, the 580 kV line from 2A thallium. And we measure the positions of these peaks in our physics spectrum, and we plot the reconstructed energy versus the literature value and the residuals of those. And so from this fit of physics data, we estimate the peak position at Q beta beta and the bias. And so we estimate a bias of minus 0.2 keV with an uncertainty of plus minus 0.4 keV from the position of the peaks in our background data. We have excluded some peaks like the cobalt-60 due to a spatial non-uniformity, and in particular one light detector having an excess contamination in cobalt-60. And the molybdenum-99 due to the fact that it's an activation product after neutron irradiation which decays away. In order to get the widths of the ROI, we go to the 2615 kV line in calibration data again. And so what we do is we perform a simultaneous unbinned extended maximum likelihood fit, which has individual components for the single Gaussian peak, but common components for the backgrounds. So for multi-Compton smeared step function background and for a linear background, linear component over here. And so from this, we extract the individual Gaussian resolutions on a by-channel basis, and then we need to scale or extrapolate those from 2615 kV to the physics data at 3034 kV. We have tested several hypotheses how to compute a scaling factor. So we have taken a linear scaling, we have taken the assumption of a baseline resolution and added a statistical term in quadrature, which is this square root term over here. And we have tried just a phenomenological second order polynomial fit as it was done in CUORE before. In terms of the models, typically the best fit is achieved with the square root model, but it's not really distinguishable from the second order polynomial fit, while the first order polynomial fit is ruled out in background data. So what we do in this analysis is we take the more conservative choice. We take the second order polynomial, which results in a slightly larger scaling factor and an estimated resolution at CUPID-Mo of 7.7 keV with these detectors. Now the next component, after having the resolution and the resolution scaling factor for CUPID-Mo, we get the background index that we expect. And so for one thing, we have an ongoing effort to construct an accurate background model simulating different contaminants out of the uranium and thorium chain in our geometry in Geom4, and then fitting all of the individual components back to our data. And so this is a very preliminary fit that we produced. And right now it's still heavily dependent on how we attribute, in particular, thorium and 208 thallium, either to near or far components. And so based on this, we get a preliminary estimate of 4 ± 2 counts per kV per kilogram year as 4 ± 2 times 10 to the -3. Sorry, 10 to the -3 is missing on this slide. I'm not sure how that happened. And we complement this approach of the Geom4 background modeling with a purely phenomenological approach, which is much simpler, but potentially approximates some more background models, some more background sources that are not incorporated in the background model yet. So we fit the tail of the 2-nu spectrum with an exponential. And so this is motivated, A, by the observation that this fits well, B, that pretty much all of the tails that we have seen in our calibration data as well can be well approximated by an exponential. And then in addition, we take a flat component up to high energy, up to 4 m.w.e. And this is a conservative kind of model for any backgrounds that we haven't included in our background model yet. So for example, 2 neutrino double beta decay pileup that coincide in time and add up to much higher energies, peaks around the 3 m.w.e. area, and so is locally rather flat, or remaining muon-induced events. Or a contamination in the crystals, beta contaminations, where the 208 thallium endpoint is 5 m.w.e. So doing this, we get a fit which is heavily dependent on the fit range that we choose, but varies between extrema of 2 to 6 times 10 to the -3 counts per kV per kilogram year. So perfectly in agreement with the Geom4 based fit model. Based on these 3 numbers, having an estimate of the background as well as the resolutions, we optimize our counting analysis by by splitting each detector-based simulated spectrum in 0.1 keV bins, and then ranking each bin that's associated now with a triplet of energy, detector, and data set in signal to background likelihood space. And so the metric that we use to maximize where to cut off this metric, which bins to accept in this background to signal likelihood space, is the mean limit setting sensitivity for Poisson counting analysis. And the parameters that go into it is 2.8 kilogram years for the final CUPID-Mo exposure, which is roughly 25–30% higher than what we had unblinded for Neutrino, and the background index, which we round to 5 × 10⁻3. So this gives quite large region of interest of 18 kV average widths. For the limit setting, we consider both the central region of interest as well as the 2 sidebands in our 100 kV blinded region. And so we construct a likelihood function, which is just a Poisson likelihood function in these 3 regions, which considers a Gaussian signal in the central bin, and then in the sideband it considers background plus about 1% of the signal, where the background is given by the exponential and flat component, just like in the phenomenological background fit before. So using Gaussian priors from the fit of the 2 new spectrum, this results in the following limit after unblinding. We've got no event at all in the central region and a single event over here at the edge of our sideband. And so this leads to a posterior distribution, which has a 90% confidence limit of 2.4 events for signal, which in turn is a half-life limit of 1.4 × 10⁻24 years. And so this includes the following systematics. It includes 0.2% uncertainty on the isotope concentration. It includes a 1.1% uncertainty on the containment, and particularly the GeO4 modeling of Bremsstrahlung and that impact on the containment, as well as the energy scale and resolution uncertainties. It includes our statistical and systematical efficiencies, analysis efficiencies, and one potential additional systematic, which comes from a potential non-Gaussianity of our peak. And so in order to estimate that, what we did is we went back to our calibration data and looked if there are any shoulders, of the peaks. And so we see that in our central ROI, we have this red part, but then if we estimate the background and extrapolate over here, we see these 2 parts. We have established that they are heavily dependent on the cuts we place and on pile-up cuts. And so while pile-up is much reduced, in principle not present in background data, we still place a conservative estimate of -2.5 plus -2.5% on this efficiency loss due to non-Gaussianity. So with all of those included, we have the 1.4 × 10⁻24 half-life limit. And so this compares to the previous results in the sense that it's 30% stronger than the best limit on molybdenum 100 before. And in this space of effective Majorana neutrino mass against the lightest mass, we place a limit which is the 4th strongest limit right now with this small scale demonstrator, which is 310 to 540 millielectron volt at 90% confidence interval, considering the following nuclear matrix elements. And so I think at this point, I'm coming slowly to a close. So this is the current best result that we have from molybdenum 100. We are presently writing the paper. We are working next on using this data to do a precise measurement of the 2 neutrino decay mode. And so with the predecessor, with the first 4 crystals, There's a recent publication out here if you are interested in this, which resulted in an estimate of 7.12 times 10 to the 18 years. There were neutrino contributions if you are interested to look that up. And finally, the next big efforts will go into really understanding what are the remaining backgrounds that we have, what's making up this 2 to 6 times 10 to the minus 3 counts per kV per kilogram year. And so this is essentially what I also have on this slide over here. Now CUPID-Mo has finished data taking. We have 2.8 kilogram year total before it cuts. We have finished up data taking with an additional calibration campaign, which should help us narrow down some uncertainties, in particular on the energy scale. So we produced a 56 cobalt source through proton irradiation at Berkeley, and then shipped that and calibrated the detectors for 2 weeks. So there is a lot of science that's still going on in CUPID-Mo. And so at this point, I would say stay tuned for more results. And I have a couple more slides, what CUPID-Mo means for CUPID, but I would leave that open to questions. And so thanks a lot.
Thank you very much, Ben. It was very nice talk. We already have one question. Chris, if you want to go ahead.
Yeah, actually, I have 2 questions, but one earlier in the slide when you were talking about your energy resolution, you mentioned an issue of sampling rate, but your pulses are rather slow. I mean, I realize that storing data isn't easy, but can't you do some calibration run with 10 times higher sampling rate and just answer that question?
In principle, so the situation that we have in the Laboratoire Souterrain de Modane in the Edelweiss setup is that we have an AC biasing, and so we are limited between the operation of our AC bias and this time scale in which we can switch the polarity. So there we can go to slightly higher sampling rate, but we will degrade the resolution for the LMO crystals. So it's a trade-off, it's an optimization game. But for the future experiments, yes. So 2 kilohertz is the minimum baseline that we're looking into for CUPID.
Okay. And you were looking at the background model for higher energy gammas. I don't even know if this is an issue, but if you looked at the rates of neutron-induced gammas, like capture gammas in your copper or whatever?
They are included, so we have some simulations for them. They are not relevant for the current, for CUPID-Mo itself. They are a small contribution in CUPID. So in CUPID, we are looking at taking the infrastructure of the CUORE experiment, which currently houses 750 kilogram of tellurium dioxide, and replacing that with lithium molybdate crystals. And so there, if we are looking at our current understanding of our backgrounds, right now, if we are taking the CUORE background model and just going to the energy of the Q value of molybdenum 100 at 3 MeV, over here, then the cryostat itself actually has a quite low background at the below 1 times 10 to the minus 4 counts per kV per kilogram year level. And the neutron capture is even below that. But in the dominating part right now is the closed copper components. And so mostly 2,8 thallium and coincidences of 580 kV to 615 kV photo plus a Compton, which in tellurium 130 would amount to 2 times 10 to the minus 4 counts per kV per kilogram year, while we have a goal of 1 times 10 to the minus 4. There is a benefit in this case for going to lithium molybdate in the fact that it's lower density, smaller crystals that we have. And so we have seen in initial simulation that the gamma interaction probability is reduced by about a factor of 3. So we get less M1 events and more higher multiplicity events from that. So this reduces a little bit and brings us pretty much to our goal with the technology that we currently have.
Thanks very much. I enjoyed the talk.
Nigel, you are.
Yeah, thanks for the talk, Ben. Really nice. I was interested in the way that you were doing the analysis on the regions of interest, where you got it broken down by crystal and data run. Are you seeing a correlation in the data runs between the various crystals? So are the data runs shifting that region of interest randomly, or are the correlations between the runs?
We haven't seen correlations between the runs. So essentially, the estimate has been done individually on a channel dataset basis. So nope, we are not.
You're treating everything as independent, basically.
Yeah.
Yeah. Okay, interesting. Thanks.
Jeter, you're next.
Yes, so I was curious about slide 22, or impressed, I guess, something. Yeah. So it looks like a pretty dramatic, I mean, what sort of threshold reduction, particularly for the light detectors, it looks like it's almost an order of magnitude in threshold?
Yes, so in principle, our derivative trigger was, so the derivative trigger that we set on the light detector, it's kind of a little bit the problem with the sampling again. So maybe if I go to my initial slide over here, we can see that our light detector pulses, we are not sampling them very well. So also triggering on them is essentially, we've got 1 to 2 samples that we can really easily trigger on. And so doing some filtering helps us a lot still in this case.
But this, I mean, this must be, to go to a, unless I don't understand, maybe it's this derivative trigger with this sparse sampling, you're saying it sort of increases the noise artificially.
Yeah, it's suboptimal, and the other thing is that we have set it at a very, very high threshold. So we use the experiment essentially in 2 ways. On the one hand side, we always trigger on an LMO crystal, and for each LMO trigger, we look at the light detector energy. And that's the main analysis for Neutrinoless FWHM. In addition, we run the light detector as their own trigger. So while the trigger threshold could be interesting for studies where we use the light detector alone, it's not relevant for the Neutrinoless analysis. And so our main concern at the beginning was to set it high enough so that we don't get any problems in the production with triggers from varying noise conditions in the cryogenic setup.
Okay. And I guess on the LMO, the reduction was still impressive, but a little more modest. Or is that a factor?
It's still a factor 10 in this case. So there are some crystals where the improvement was modest, some crystals where it was quite strong.
Okay, and I was going to ask if you understood the sources of that noise and for those cases.
It's so one of the sources of noise that we have seen in our setup, it's essentially we have a lot of noise which is characterized on a tower by tower basis, and so we have a suspicion that the dampening of some of the crystals could have been improved, and between the wiring and the vibration isolation, there is some mode where we actually get some resonances. And so we've got periods where noise pops up more strongly on a single tower. And so in order to avoid issues with that, we just had very high trigger thresholds.
What sort of frequencies do you get for that?
I would need to look it up. Sorry.
Thank you.
Are there any other questions? So have you, while waiting for other questions, do you see any, in terms of radioactive background, any difference from the top detector to the bottom detector in terms of DRU?
It's something that we have been looking into. We don't really have too much statistics. So mainly in terms of localizations, what we found so far is we found one hotspot of cobalt-60, which is located on one light detector, which also has a very interesting signature, with the beta being seen on the light detector and the gammas being seen in the adjacent crystals. In terms of splitting the background modeling effort by different geometries, and in particular upper to lower layer, we haven't seen significant differences.
So the lead sheet now is matching again?
It should be decently well matching.
Okay. Any other question or comment? Eve.
Sorry, I have one question. Did you say, I may have missed it, but did you say you're using molybdenum 100, is the same enrichment as NEMO-3? Or is it, so I guess my question is that, is the background level of molybdenum 100 is cleaner than NEMO-3, or is it similar, you would expect similar background as NEMO-3 in the molybdenum itself?
So the molybdenum itself, we took the foils from NEMO-3, so we got the actual material from NEMO-3, but then it underwent purification and the crystal growth process. And so in terms of
sorry, I missed that. Okay, so I think that was something I missed. So I think I got my answer. Yeah. Okay. So how much cleaner that would be compared to NEMO-3?
So in terms of backgrounds, right now, let me go to maybe, let me see. Yeah, that plot will do. So right now, most of the backgrounds that we are concerned about is anything that's in this high energy region over here. And so we've identified, we've investigated the topology of those events in detail after unblinding. And so we found that one of those events is consistent with being a 212 bismuth alpha, and then 120 seconds later being a beta from 208 thallium. So that's one of the high energy events. Other than those, we've got a couple of hypotheses that we know contribute at some level, but we haven't nailed it down exactly. So one more background that we expect is 2 neutrino double beta decay pile up in time. So just randomly two of these decays coinciding and leading to a much larger energy deficit. That one we will try to address by actually injecting two new events into our data stream and just measuring how many of these events survive our pulse shape cuts on simulated data. In addition, we don't know the efficiency of our mu and anti-coincidence cut, the rejection efficiency. We know the signal efficiency, but not the rejection efficiency. So that's another hypothesis for background at the levels we are looking at. And so we're in this range of around 4 times 10 to the minus 3 counts per keV per kilogram year. And there are some tails that we also know from 2A toluene, so some tails that extend here in this plot. But in the end, all of those are at the probably at the 10 to the minus 3 level, and so they're quite hard to disentangle.
Thanks a lot. Thank you.
So if no other question, I would like to thanks Benjamin again. Thank you a lot. And if you can send me the slide, that will help.